So today we have the pleasure to have Florent Bouchard from CNRS and L2S in Central Supélec. We'll talk about the Riemannian geometry for data analysis. Florent, the stage is yours.
Okay, thank you. Hello everyone. So thank you for inviting me to give this talk, and thank you for attending. So as said, I'm going to talk about Riemannian geometry for data analysis with an application to blind source separation and low-rank structured covariance matrices. So first, an introduction. So in fact, for statistical data analysis, what we aim to do is that given some data, we aim at finding some parameters, theta, that statistically characterize this data. And in general, what we have is a model, a statistical model, and this model can be represented through a cost function. And we, given some data x, we aim at finding the minimizer to this cost function f here by solving this optimization problem. And so usually with real life data, we have some constraints, some structure, both for the data, which might, for example, be positive or something like that, and on the parameters. So for example, if we have some data that are characterized with the covariance matrices, we have some positive definiteness and stuff like that. So both the parameter space X and the data space X and the parameter space M are manifolds here. Okay, so the aim here is to exploit geometry and the structure of both the data space and the parameter space, and with this structure have some contribution on 3 points. So on the modeling, in order to design some appropriate cost functions, for instance, we can have centers of mass, and on optimization as well, because the cost, we can exploit the structure to optimize the cost function and to remain in the manifold and have appropriate methods. And also there is a framework that deals with performance analysis of our estimators, in particular defining geometric error measures and the associated performance bounds. Okay, so in this presentation, I will first give you an introduction to Riemannian geometry and optimization, and then we will deal with approximate joint diagonalization and with some performance bounds for low-rank structured elliptical models. Okay, so first, for the Riemannian geometry and optimization, we are dealing with manifolds. So a manifold is a nonlinear space, like here, which is locally diffeomorphic to the Euclidean space with the dimension d, which corresponds to the dimension of the manifold. And what we can see from here, it's a space that locally looks like the Euclidean space, and in particular we can define a tangent space at every point of the manifold. Okay, and from there we can have defined some derivatives of any curve on the manifold. So we can have some curve and take the derivative at the classical definition, and it gives from there the tangent space as the sets of all the derivatives of any curve going through some point theta. Okay, And then what's very interesting is to define a Riemannian metric, because it allows to have a relative position and the length of the different tangent vectors. So a Riemannian metric, it's an inner product on the every tangent space, and it's very helpful, and it also allows to define objects such as geodesics on manifolds, which generalize the idea of straight lines, but also take into account the constraints and the curvature of the manifold. And as for the Euclidean case, what we use is to define them is a differential equation. They are defined as curves with zero acceleration on the manifold. And this operator here is very specific to the manifold and depends on the Riemannian metric. Okay, and then from there we can simply define the Riemannian distance by measuring the length of the geodesics according to our chosen Riemannian metric as well. So the choice of the metric is really central here. Okay. So what we can also do, define some very specifics on manifolds. And so the goal is to find the minimal to a cost function f. And the idea is that starting from some point theta, we aim at finding a descent direction, so a tangent vector such that the directional derivative of f is negative, so which translates into a diminution of the cost function. And for that, a very useful tool is the gradient, which is defined thanks to the Riemannian metric again, and with this equation here. And from there, the idea to minimize a cost function is that we select some descent direction. So for example, in the simple case of the gradient descent, it's just the opposite, the scaled opposite of the gradients, but we can have some more complex options. And then once we have the descent direction, what we do is that we use a retraction, which allows to get a point from the tangent space onto the manifold. Okay, and that we can reiterate this operation until we go to a critical point, so when the gradient vanishes. Okay, so that will be all for this short introduction on Riemannian geometry and optimization, and now I'm going to talk about some of my PhD work, which is on approximate joint diagonalization for blind source separation. So the idea of approximate joint diagonalization here is that we have a set of K symmetric positive definite matrices, and we aim at finding a joint diagonalizer B, so a non-singular matrix B, such that the transformed matrices B, C, K, B transpose are as much diagonal as possible. So what we can do to formulate this problem is to define a diagonality criterion f of the set of transformed matrices, and define B as the minimizer to this cost function. Okay, and this has a central application to blind source separation, where we have some observation X, which results from the linear mixing of some sources with some matrix, non-singular matrix A. And in fact, with by jointly diagonalizing covariance matrices of the observation, we can obtain a matrix P that corresponds to the inverse of the mixing matrix, and that allows to retrieve the sources. Okay, so there are many applications, and in particular for electroencephalography, where we have different sources in the brain that propagate through the brain and the skull to electrodes, and this is typically this problem here that we have. So joint diagonalization allows to solve these kind of things. And one thing that we proposed during my thesis was to have a geometrical modeling of the problem. And the idea in this setting is to look at the space, and the goal is to get the covariance matrices CK as close as possible to the set of diagonal positive definite matrices. So the diagonality measure of the transform matrices becomes their relative position with respect to diagonal matrices. Okay, so with this modelization, an appropriate criterion is to take F as the sum of the divergence between the transform matrices and some target diagonal matrix on the set of diagonal matrices. So here the divergence will define how we are going to try to get closer to the diagonal matrices, and the target diagonal matrix on the set of diagonal matrices will define where we want to go on the set of diagonal matrices. Okay, so once we have chosen a divergence, there is a natural choice for the target matrix, which corresponds to what we can call the projection of the transform matrix here onto the set of diagonal matrices, which is given by this optimization problem here. Okay, so in my work we have considered a lot of different possibilities, and the first interesting thing is that with this formulation we get the two classical criteria used for diagonalization. The first one, which is the Euclidean distance, so for the least squares criterion. So we have the Frobenius distance here, for which the closest diagonal matrix to matrix C is given just by taking its diagonal parts, and also by taking the left Kullback-Leibler divergence, which is given here, which is non-symmetric, so that's why left. We obtained the usual log likelihood criterion, for which we also have the diagonal part of the matrix C as the closest diagonal matrix. And what's interesting also is that it's only for these two very classical criteria that we have obtained that the closest matrix the closest diagonal matrix to a matrix C is simply diagonal parts, and we have considered other measures. So the first one is to just take the Kullback-Leibler divergence and take it the other way around. So we have a right measure where this time the closest diagonal matrix is given by the inverse of the diagonal part of the inverse, and the symmetrized measure. So if we take only the arithmetic mean of the two previous criteria, we obtain a new criteria for which this time we have the geometric mean of the two previous diagonal matrices. Okay. So we have also considered other divergences, so the natural Riemannian distance, distance, which corresponds to the Fisher distance when we consider Gaussian covariance matrices. And also we have considered the log Euclidean distance. So it can be, for instance, seen as a linearization of the natural Riemannian distance around the identity matrix. And we also have considered the Bhattacharya distance. So this is a very interesting distance because it shares a lot of properties. It's close to the Riemannian distance, except that it's computationally cheaper, so might be better for real-life applications. And also we have considered the Wasserstein distance, which is quite trendy from the optimal transport field. So from there, we have then tried all these different divergences to perform approximate joint diagonalization on simulated data, and we have simulated some matrices, so some target matrices plus some noise here, and to measure the performance, we have used a classical Moramari criterion, which measures the degree of similarity of BA with some permutation matrix multiplied by a non-singular diagonal matrix, which correspond, if we have a matrix of this form perfectly, we have a perfect solution to the problem. Okay, and so here are some results. So the Moramari criterion, the more we are at the bottom here, the more the recovery is good. So the better is the recovery, and sigma here represents the signal to noise ratio. So the further we go on the right, the easier it is for the methods to recover the data. And basically here we have two groups of methods. So the Frobenius and Wasserstein ones that perform well when the signal to noise ratio is good, but they behave poorly when it's not the case, and the other methods are more robust to this parameter here. And the right Kullback-Leibler divergence on this data is particularly efficient here. So then we did some experiments on real data, so electroencephalographic data. We considered the SSVP data. So basically what we have here is we have a light blinking, and in fact there is a physical phenomenon which makes that the brain blinks at the same frequency as the light it is exposed to. So the data we considered were recorded with 8 electrodes at around the visual cortex, and we have 4 different experimental conditions. So with several frequency for the light to blink and a rest condition. So what we can see from the data is that on the electrodes we observe the signal that we expect. So here it's the power of the signal as a function of the frequency. And at each frequency of interest or each condition, we observe that there is some signal, and we also observe here and here particularly some activity which corresponds to a rest activity of the visual cortex. Okay, So when we perform blind source separation by diagonalizing some covariance data, some covariance matrix of data, we obtain two very good sources which correspond to the sources that we observe in the raw data. So a source which corresponds to the SSVEP, so where we have the signal at each frequency for the corresponding experimental condition, and no signal elsewhere. So it's quite good, and also a source that is consistent in every condition, and which corresponds to the rest of the visual cortex. So some baseline activity. Okay, so what we can do here to measure the performance of our different algorithms is to measure how discriminative is the separation. So what we did is that we measured the power of the source at the target frequency, and we divided it by the whole power around over all frequencies. And what we can see with this performance measure is that for the 13 Hertz condition, we have very good results for every methods, but when we go further in frequencies, so to the 21 Hertz, the Frobenius and Wasserstein methods don't perform that well, and which is quite interesting because the signal to noise ratio in this experimental condition is lower than for the 13 Hertz. So we observe the same behavior as for the simulated data, and these methods give less consistent results. Okay, so that will be all for this part, and I will now show you some results for performance bounds, so interesting Kramer-Rao bounds for low-rank structured elliptical models. So the first, when we have some data that have a law with some parameter theta, and that we have a corresponding log likelihood function. So the estimation problem is that given some data, we aim at minimizing the negative log likelihood function over theta. And we have access from statistical literature to a performance bound, which is the Kramer-Rao bound, where in fact the error between the real parameter and its estimator is greater in expectancy to some inverse of some matrix, which is the Fisher information matrix. And this classical results in Euclidean spaces can be extended to manifolds. Okay, so for classical case, the error is often given by always given by the difference between theta and its estimator, where we can take the Euclidean norm, and the Fisher information matrix is given by this formula here. And if we want to take a more general case into account, where we can take constraints and invariances of the model, then we can generalize these results to a Riemannian manifold, where here the error measure will be given by the distance function on the manifold, the squared distance function, and the corresponding Fisher information matrix is given by this formula here, where this is the Fishermetric, which is given by a very similar object at this one, and EI and EJ corresponds to an orthonormal basis of the tangent space associated to the Riemannian metric, which corresponds to the square distance defining our error measure. So for instance, we applied this on the elliptical distribution with a low-rank structure. So the elliptical distribution, we have some data which have some covariance matrix, and this log likelihood function, where we have this function g here, which depends on the choice of the distribution. So for example, if we take this formula, we have the Gaussian distribution, but we can also consider other distributions, such as the generalized Gaussian, the students, the K distribution, and others. And for all this class of distributions, so the Fishermetric for on the set of positive definite matrices is given by this formula here. And in this work, we have considered a low-rank structure, which is very adapted to the case where we have a few data. And our covariance matrix at this form, where this is the identity matrix, and H is a positive semi-definite matrix of rank K, which is assumed to be known here, and it follows that what we need to study is the geometry of the manifold of positive semi-definite matrices of rank K. And this geometry is not very easy to define, and several possibilities have been proposed, but there are none that are ideal, because there are none where we have a good distance function and all the geometrical objects that we need. Okay. So in fact, what we considered in this work is a quotient to exploit the singular value decomposition. So every matrix H can be decomposed in U sigma UH, where U is a matrix, orthogonal matrix in the Stifel manifold, so a rectangular matrix, and sigma is a positive definite matrix of size K. And with this model, the problem that we have is that there is this invariance. So for every unitary matrix O, this point is strictly equivalent to this point. So in fact, we have to take that into account and consider the quotient, which considers every fiber here as a point. So what we can do is then look at the Riemannian geometry of our quotients. So to do that, we consider the geometry of the embedding space. So the space, the product manifold of Stifel with positive definite matrices. So we have this formula here for the tangent space. We choose this metric to work with. So this is the canonical metric for the Stifel manifold, very classical. And this is a metric which an affine invariant metric on the set of positive definite matrices, and which is related to elliptical distribution, as we saw before. And okay, so then to describe the geometry of the quotient, the first thing to take into account is the invariance fibers here. So to describe the tangent space of our quotient, we can consider the vertical space, which is the tangent space to the fiber, and the tangent space of the quotient is then given by taking the orthogonal complement to the vertical space, which gives what is called the horizontal space, and which contains proper elements representing the elements of the tangent space. Okay. So the problem that we have is that the Riemannian distance is not known in this space, and to deal with this issue, in fact, what we have proposed, what Bonabel and Sepulcre proposed before, is to consider an alternative horizontal space. So we don't take the orthogonal complement to the vertical space, but we still take a complementary space, which is not orthogonal. So the counterpart is that the problem is that we don't have a distance function, but divergence, which is given by this formula here. But we can still work with it, and in fact still define a performance bound. To define it, we have this Fisher information matrix here, where so the Fisher metric is defined as in the classical case, and for the orthonormal basis, this time we take the orthonormal basis of the alternative horizontal space that we have considered, and which is given by this formula here. And it only remains then to define the Fisher metric on our manifold, and to do so, we have this log likelihood function on the manifold, where we have this function that gives our positive semi-definite matrix given here, and its derivative. And in fact, we have shown that the Fisher metric can be obtained by taking this formula, where, as shown in the introduction of this part, the Fisher metric is given. So then we have made some experiments, some numerical experiments to confirm that our performance bound is accurate. And to do so, we have simulated a covariance matrix with a low-rank structure like that, where in fact the important thing here is that we have chosen the condition number of sigma with respect to inversion, and then we have normalized its trace in order to control the signal to noise ratio with this parameter sigma here. And we have done 500 Monte Carlo over sets of randomly generated samples, with the samples generated according to the T distribution, with 2 different values of degrees of freedom. So D equal to 3, for which we have highly non-Gaussian data, and D equal to 100, which is almost Gaussian. Okay, so what we have in the results is, the first thing is that in both cases, our estimators reach the bound, which is what we hoped for. And in the non-Gaussian case, in brown, you have the Gaussian estimator, so the projected sample covariance matrix, it doesn't reach optimal performance, whereas some other estimator obtain the robust M estimators. So Tyler reached the bound, and in the almost Gaussian case, the projected sample covariance matrix gives the best result. So that will be all, and now I will give you some conclusions and perspectives. So, in fact, I do believe that Riemannian geometry is quite a powerful tool for signal processing and machine learning, because we can exploit both the intrinsic structure of the data that we have at hand, and also of the parameters. And also, it's very modular, and we can use it to do almost everything we need to do, which are modeling, optimization, and performance analysis. So it's quite powerful, and but we need to use it wisely, because if we have Euclidean data and Euclidean parameters, it's a bit overkill. So what we can use Riemannian geometry when the data and the parameters have particular structures. So we have some constraints, some invariances that we want to take into account, and also when there is some metric, some Riemannian metric, which is very interesting with the model that we consider. So, for instance, the Fisher information metric, when we deal with likelihood and distribution. Okay. So the issue also, the problem is that sometimes it's very hard to deal with a Riemannian geometry, because the geometrical objects can be very complicated to obtain. But as we saw, it's also sometimes possible to go beyond these problematic and to choose alternative geometrical objects which can provide efficient objects and obtain good results. Okay, so thank you. That will be all for me.
Thank you very much, Florent, for this very nice talk. So is there any question in the audience?
Yes, Thomas, a couple of questions. May I?
Yeah.
Go ahead.
Yes. Okay. So thanks, Florent, for the great presentation. So the first question, which is maybe a quick question about the EEG SSVEP. You quantify
Yes.
the performance by the ability to find only one peak in the spectrum, but shouldn't you have also harmonics when you do SSVEP?
Okay. Yeah. You are right. This is something that might happen, but not always. So we add a close look to the data before choosing to not take the harmonics, because they were not present in the data that we have studied here.
Okay. I've got another question. I don't know if I'm allowed. So kind of related also to the first part, where you show this benchmark when you change the different criteria to recover the in the approximate joint diagonalization example, you have these different criteria that you consider.
Yes.
And so kind of two nested questions. So you find different results. You use this metric, so this this, I don't remember how the Morimaki
criteria, yes.
Morimaki criteria. So the first question is, you in the end you use different optimization strategy for the different metrics, and you have to stop the convergence of your solvers kind of using different criteria. So I'm just wondering, is it possible that the differences between the criteria is coming from some kind of early stopping of the algorithms?
Well, in fact, the criteria here, the different criteria is the cost function only. But in these experiments, the optimizer is the same for every cost function, and the stopping criterion is the same for every cost function. So,
yes, but for example, if you look at the norm of a gradient, for example, it's not really comparable if you change the.
We also took a stopping criterion that is external to that. It was more the distance between two iterations that we chose to take the stopping criterion, and we took very small tolerance. So I'm pretty sure that the results that I have here are do not really depend on the optimizer.
Okay.
But of course, the thing that they depend on and quite important here is the model that we chose for the simulated data, and in particular, I did not take time to really explain this. But the diagonal matrices here have a decreasing power of spectrum, and we took a Kidder distribution with extensity 1, and we divided it by the position on the matrix. So the pth element is divided by p. So it's also something to take into account because if we take a different way to simulate the matrices, the results might be very different, and the results with respect to the different criteria might be very different. Also, so here we chose to take some matrix with some perfect target matrices plus some noise, and we have these results. But we could also have considered taking this covariance matrix here, generating some data, and then estimating the covariance matrices, which is closer to a real-life scenario when we have some data, which we didn't do. And in this work, at least, and it would also change the results a lot.
Okay, thank you very much.
So maybe if there is time, I'll ask just maybe one or two questions. Thanks again for the talk. Yeah, the first question in this first part on blind source separation, you mentioned robustness at some point. So I mean, in each example that you gave, you minimize the sum of squared errors, right?
Yes.
And it's just about how you measure this error, which divergence you use.
Yes.
So what about taking the sum of errors without the squares?
Without the squares. So I did not try that. I could do some, but for instance, for centers of mass, this is something that has been a little studied, where in fact, if you take the square distance, you have what we call the Riemannian mean, and if you don't take the square, you have the Riemannian median. So this is in fact something that could be very interesting to look at, but I did not take time to look at that during my PhD. But in fact, yes, it could be interesting.
Yeah, okay, because I mean, you can also take Huber losses, for example, which interpolate.
Yes.
Because if you take the sum of squares, then the sum without the squares, you will have a bias towards the some kind of median.
Yeah.
Okay, and the second question maybe about the, I mean, it's more general. You mentioned the Fishermetric in the second part of the talk, and in general, what does it do? So I understand that it's a way of putting some Riemannian structure on the parameter space when you have a parametric model. But what's the main advantage of this? Does it make the likelihood geometry simpler? Does it always imply that, I mean, I know that it's not true, but that the likelihood or log likelihood function always becomes geodesically concave with respect to this metric? I mean, what does it do exactly?
So what it does, for instance, if we just take here this slide, so the first thing is that this is the Fishermetric is the metric which is associated to the likelihood, the log likelihood. So it is the Riemannian metric which is associated to the distribution that we consider. So one can expect this metric to be the best one that we can deal with when we consider some estimation problem with some distribution. But it's not. The thing is also here the Fisher information matrix will be equal to the identity, because so it is adapted to the geometry, but it does not ensure the distance. For instance, the distance function of a Riemannian manifold is not always concave. So even if we take all the good geometric tools and objects on the manifold, we do not have the insurance of simplicity and perfection for the tools such as concavity or stuff like that. So it might still be hard to deal with the objects we are interested in. And yes, but maybe it's the best. It's kind of according to the model, the best metric that we can have. And also just say there are for instance, there is an online algorithm by Salem Said in Bordeaux, where the convergence proof is based on the fact that we have the Fisher metric as the metric for optimizing.
Okay. All right, thank you very much.